Hi, this video introduces some terminology used with graphs. Graphs have been studied for a long time in mathematics. There's a whole discipline of graph theory in math that deals with graphs. So there's quite a lot of terminology that has arisen for describing parts of graphs and situations in graphs. A vertex is one site in a graph. We draw those as the circles. Remember that the plural of vertex is vertices, and every vertex is a math object. So it could be a number or some other mathematical object, but often the vertices are the set of indices 0 through n minus 1. So if n is the total number of vertices, we often number these the same way that we number array indices 0, 1, 2, 3, 4. An edge is a connection between two vertices. A directed edge, which is drawn like an arrow, as in this sketch here, it would be defined as a mathematical pair. The math pair I comma j defines a directed edge from I to j. So this defines a one-way travel. For example, the pair 4 comma 0 would be the math object saying start at 4, end at 0, and that's a one-way trip. You're only allowed to go from 4 to 0, not 0 to 4, not the other way. We call the I the source vertex, the origin of the edge, we call the source. And j is the target of the edge. It's where the edge ends. We use the word ends to refer to both the source and target together. Sometimes it's convenient to talk about both of the vertices that an edge touches, and we call those the ends. So this edge I've been pointing at, the ends of that edge are 4 and 0 together. So we've been talking about directed edges. A directed edge is a one-way connection. So far, all of the examples have had directed edges, and we draw those as an arrow to make it clear which way the edge travels. But there's also such a thing as an undirected edge. An undirected edge defines a two-way connection where you can go in either direction. We define this mathematically as a set of two elements, I comma j. So the set I comma j is an undirected edge between I and j. So over here in the sketch, the set 1 comma 2 would define the edge that goes between 1 and 2, and that means that you can travel between 1 and 2 in either direction. We use a math set here because in mathematics, a pair has a notion that the first element of the pair is distinguished from the second element of the pair. So the pair I comma j says that I is special in some way relative to j, I comes first. And that's how we keep track of, between these two vertices, which one is the source and which one is the target. In a mathematical set, there is no such distinction. If a set has two elements, there is no notion of a first or second element of the set. They're all just in there. So that's a good way of modeling this situation where there are two ends of an edge and they're connected, but there isn't any distinct beginning or end. They're both just two connected vertices. For that reason, we use the word between. With a directed edge, we say a directed edge goes from a vertex to a different vertex. An undirected edge goes between two vertices. It connects them in two ways. We draw an undirected edge as a straight line segment with no arrowhead to make it clear that this is a two-way travel. It still has two ends, so this edge here between 1 and 4, the ends are vertex 1 and vertex 4. And we can use this word directed or undirected as an adjective on the whole graph. A directed graph is a graph where every edge is directed, and an undirected graph is a graph where every edge is undirected. Okay, so we've got some more terminology dealing with how vertices relate to directed edges. The outgoing edges of vertex V are the directed edges whose source is V, basically the edges that start at V and go outward. For example, 3's outgoing edges are the edges to vertex 1 and the edge to vertex 4. The incoming edges are the other way. The incoming edges of vertex V are the directed edges whose target is V. So the incoming edges of vertex 1, there's two of them. There's the edge from 0 to 1, that's an incoming edge to 1, and the edge from 3 to 1, that's the second incoming edge to 1. A loop edge is something that's allowed. It is a edge whose source and target happen to be the same vertex. So here I added a loop edge. It starts at 4 and ends at 4, and that's allowed. In some applications of graphs, we want to have the ability to represent that kind of loop. For example, in the road network, we have loops like that. There's a cul-de-sac in some neighborhoods, and that's a little stretch of road that starts and ends at the same intersection. Loop edges are also possible in undirected graphs. Okay, adjacent and incident are ways of talking about what touches what in a graph. So adjacent to is a relationship between two vertices. Vertex V is adjacent to vertex W if there is an edge from V to W. So it's a relationship between two vertices. It's basically the neighbors. So in a undirected graph, it's a little simpler. The adjacent vertices of 4 are all of the vertices that are one edge away from 4. So that would be 1, 2, and 3. Vertices 3, 1, and 2 are all one edge away from 4. So we would say that 4 is adjacent to 1, 4 is adjacent to 2, 4 is adjacent to 3. Uh, in a directed graph, it's a little trickier because of the direction. So if there's an edge from V to U, V is adjacent to W. So there's an edge from 0 to 1, so 0 is adjacent to 1. There's an edge from 3 to 4, so 3 is adjacent to 4. It's not true that 4 is adjacent to 3 because there is not an edge from 4 to 3. So in a directed graph, the order matters when you say this phrase. It's a little tricky, so we try to not do this more than we have to. So this is not necessarily a symmetric relationship. But just because 3 is adjacent to 4 doesn't mean that 4 is adjacent to 3. But in an undirected graph, the order doesn't matter because of undirected edges. So it is a symmetric relationship. If 0 is adjacent to 1, then 1 is certainly adjacent to 0. Incident to is the word we use to say when a edge and vertex touch each other. So adjacent is between two vertices, incident is between a vertex and an edge. Edge E is incident to vertex V if V is one of E's ends. So again, that's a relationship between an edge and a vertex. So this edge here is incident to vertex 4 and incident to vertex 3. Down in the undirected graph, this edge in the top right corner is incident to vertex 1 and incident to vertex 2. It touches those vertices. Degree is a way of counting how many edges are incident to a vertex. So the degree of vertex V is the number of edges incident to V. We end up needing to use this quantity a lot in our math, so we have a mathematical abbreviation for this, DEG of V, deg of V is the degree of V. So for example, vertex 4 in the undirected graph has a degree of 3 because 3 edges touch that vertex. Vertex 0 in the directed graph has a degree of 2 because 2 edges touch vertex 0. Basically, you count the touching edges. In a directed graph, sometimes we want to distinguish between the number of incoming and outgoing edges. The in degree of V is the count of V's incoming edges. So for instance, 3 in the directed graph has a in degree of 1 because there's only one edge coming into 3. And symmetrically, the out degree of V is the count of V's outgoing edges. That same vertex 3 has an out degree of 2. There are 2 edges coming out of 3. Just as a preview, part of the reason why we're highlighting this now is because there's a data structure called an adjacency list we're going to cover soon, and some of its operations take big O of degree of V time, so that's why we're defining what degree is at this point. Path, cycle, and simple path are ways of describing basically a legal travel through one of these graphs. Mathematically, a path is a sequence of vertices, v0, v1 through vk minus 1, such that each vi is adjacent to vi plus 1. That means that there is legal travel from one vertex to the next. Intuitively, that's a legal trip through the graph. For example, a legal trip through the directed graph could be 0, 1, 2, because I'm following directed edges the way that they point. A path through the undirected graph could be 0, 3, 4. That's a legal path following edges the way they go. These paths don't necessarily have to start at 0. Another legal path could be 4, 1, 2. A cycle is a special case of a path where v0 and vk minus 1 are the same. In other words, it's a path that starts and ends at the same vertex. So for example, in the undirected graph, I could form a cycle by going around this square here. So 3, 4, 1, 0, 3. I started and ended at 3, the same vertex. Or in the directed graph, I could go around this triangle. So 3, 1, 2, 3. I started and ended at 3. A simple path is a path where every vertex is unique. Another way of saying what a simple path is that it's a path that does not have a cycle inside of it. So the paths I've described so far, except for the cycles, were simple. You know, another simple path through the directed graph might be 0, 1, 2, 3, 4. I never repeated any vertices. But I could form a non-simple path by going through a cycle. So I could loop around this 1, 2, 3 triangle. So for example, if I start at 0, let's go 0, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. That's a legal path because all of those transitions were legal according to the directed edges, but I repeated 1, 2, and 3 a bunch of times because I went around that cycle. So that would not be a simple path. Reachable is a way of describing which vertices can get to which other vertices. Vertex D is reachable from vertex S if there exists a path from S to D. Here, S is for start and D is for destination. So, for example, in the directed graph, I don't know, 4 is reachable from 1 because there does exist a path from 1 to 4. I can start at 1 and follow directed edges and arrive at 4. And in a directed graph, the way that you get unreachable vertices are if you have a kind of a dead end. So this example in the bottom right here has this kind of dead end. 2 and 3 are kind of down in this basement here. If you follow the 0 to 2 edge, there's no way of getting back up. So 1 is reachable from 0. I can go from 0 to 1. 3 is reachable from 0. I can go 0 to 3. However, 1 is not reachable from 3. If I'm stuck down here in 3, there's no way of getting back upstairs up to 1. So some vertices in a directed graph can be unreachable. The same concept carries over to undirected graphs, but since undirected graphs allow travel in both directions, it's kind of tougher to make vertices be disconnected or unreachable. So vertex D is reachable from vertex S if there exists a path from S to D. That's the same definition as before. In an undirected graph, unreachable vertices have to be in a different component. And what a component is a set of vertices that are all reachable from each other. So I've formed two graphs here. Each graph has this dashed line around it. So in the top right corner, this is one graph with vertices 0 through 4, and all of the vertices are in one big component because every vertex is reachable from every other vertex. In the bottom right corner, I formed a different graph object. Everything in the dashed line is one big graph, and they're not all connected. The vertices are not all connected. That's actually legal. There's nothing in the definition of graph that says that all the vertices have to be connected. So 1 and 2 are one of the components of this graph. 0, 3, 4 are the second component. So there's kind of these two islands or continents. There's the 1, 2 island and the 0, 3, 4 island. 1 and 2 are connected to each other. 0, 3, and 4 are connected to each other, but there's no connection between those two components, we would say. So an undirected graph always has at least one component, but it may have multiple components. A connected graph is a graph where all of the vertices are in one component. So the top right example is a connected graph. The bottom right example is not a connected graph.